Okay, and that actually the number of injectors define the capacity, the water disposal capacity that I have. So if something happens with one of these injectors, you're losing your water disposal capacity. And then then you are forcefully, you have to reduce the oil rate or gas rate, oil rate. Okay. Then, then we had this class we had on the 17th. Okay. And just what we have done in this class was to make using trying to develop an analytical equation for simply for the profile for the rate of the field, okay, for the profile of the field. And we said if you are operating in plateau rate, first we make some assumptions, right? We assume it's an undersaturated oil reservoir. We took almost the simplest case that we could find. Okay, we took an undersaturated oil reservoir. We have a very strong aquifer supporting pressure. Then we said we can express reservoir pressure as a function of initial reservoir pressure minus a constant times how much, what is the cumulative production, how much I produce from the field. That constant A, we said, well, if we have an aquifer, depends partly on the volume of oil we have in place and also on the volume of this aquifer supporting and some fluid properties, the compressibility of the oil, compressibility of the water, porosity, and so forth. So then we got our equation for PR. That was in the simple analog we were using. It's not here, but on the previous class of our production system. We said our analog looks like that. The reservoir has two parts, storability, the change in pressure when I drain material. That's that first equation. And then I have one more equation which tells you the flow, the pressure drop in the flow. How much does it take for the oil or the gas to go from the reservoir towards the wellbore? For that we have used another equation, which is simply, we just had some discussion on IPR, but when we talked about oil, we can use a simple linear equation, undersaturated oil. Very simple case, but just was to derive analytically to get to something where we calculate the rate of the field. And then we had one more assumption. We said we have defined on this bottom hole pressure can have any value. Okay, but I have defined a minimum value that it can have, that is the minimum flowing bottom hole pressure. And I did the comment that if you have a system where you have a pump, you can control that pressure. And in the lowest value you can have is the saturation pressure, just to make sure that you don't have any gas coming out of solution and into the pump. Okay. By using these two simple equations, we get to this equation that I told you is the potential of the field, where we have, not this one, but the one above, where we have the maximum rate the field can produce at a given cumulative production. If I haven't produced anything, this number will be maximum, will be equal to the initial. And then if I start producing, the reservoir pressure will decline, and then I will be able to produce less and less. The nice thing about the equation is that we have the rate, and here we have the integral of the rate. So that we suspect that we could somehow manipulate that equation to find an expression for the rate. We have an equation, basically the factor, the unknown that I want to clear, I have it everywhere. Okay, so I can express that unknown in terms of the variables that I have. So we have done that. First we said for the plateau period, okay, and that was a bit difficult to grasp for some of you, but for the plateau period, it means that on that curve, that I will reach the end of the plateau when the potential is equal to the plateau rate. That means the maximum that I can produce is equal to the rate that I want to produce in plateau rate. Okay? That's how I find the NP on that curve. I call it NP star. By doing that, you find out an expression for the duration of the plateau. That in our case we can have, it's nice to have that simple model. We can see what affects that plateau duration. Okay, you see that you have, for example, the plateau rate. If I increase it, it makes if I increase it, it makes the length of the plateau shorter. Okay, and that was one trend that we intuitively had. If we make the height of the plateau, if we make it higher, then we will be shorter. If we make it lower, then it will be longer. It will produce for longer time. So as we can see from that equation, and also one more thing was that the number of wells, and that was not very clear, right, from this expression. But if we multiply both terms, okay, you see that actually the number of wells here, it gets cancelled on the first part, and on the second part it ends up down here. So if I increase the number of wells for a fixed plateau rate, that means this part is becoming, all of this summation is becoming more positive, bigger. That means the plateau duration is increasing. Okay? Intuitively, there are some that have, some problem visualizing that, but basically that's, from this simple model, that's what it gives. And then we went one step further. We know that after I reach that point of intersection, the end of the plateau, I enter in decline. And in decline, what we discussed, I'm always producing at the potential rate. And for that, okay, here decline, here I'm always at the potential. So I came on my original equation, I substitute two periods, NP, I have a plateau period, I have a potential period, and then I found a solution for that equation that was actually an exponential. Okay? If this potential looks like a straight line, this integral will be an exponential function. Okay. We can do that only for that case because it's very simple. Undersaturated oil, we have undersaturated productivity, a straight line, everything is very simple. The case that you're doing now, that you're working with in the exercise, is a dry gas case. And you can start putting equations one inside the other, but you don't get such a nice expression. But the idea is that you look at the effect that you have on the plateau rate, on the plateau duration, on the number of wells, on the plateau duration, and so forth. You cannot use these equations for the dry gas case, okay? But it helps you to understand what should happen. Okay? Any question about that?
Is that the same as the Arps equation for the exponential form on the decline?
Yeah, you can say, but actually ARPS was completely empirical.
Yeah.
Okay, so here you can say some justification that it comes also from physics. Okay, it comes also from the equation. Okay. And actually what I was also saying last class, that many people just try to fit exponential equation to the decline. But you have to be careful. The exponent of that decline depends very much on some things that you're going to tell me about. Okay? Okay. So before we close, any question? No? Okay. See you tomorrow. It's at 10. Okay?
Excuse me, can I just ask you something?